interest theory and the basics of the mathematical finance. But again, here's only some small pieces of this theory, small parts and small, basically examples. Okay, what is arbitrage? Arbitrage is a possibility on the market to get a riskless profit with non-zero probability. So if you have a strategy or you have some rule that makes it possible for you to get profit, riskless profit. So the profit without with probability zero, that you can lose something. So you can only win, and this arbitrage, this possibility should be precluded on the market. This is not, because otherwise this ideal market, you would have, some people would have profit and some people will have losses with probability 1, so to say. And this is what happens in reality. We don't know. So of course we see that some people really get a lot of money. Some banks, for example, lose a lot of money. But at least what is not arbitrage is a basic property of the ideal financial market. This property, if you propose some model for financial market, or you propose strategy, this strategy should be non-arbitrage strategy. Some examples: if you buy and sell a stock, one stock and buy another stock at different prices, then some possibility of arbitrage. If you have two portfolios with the same value as the maturity and different values for some another time before maturity, it also leads to arbitrage. More details about it. So let us consider, the last point about two portfolios. So let us have two portfolios, A and B, with current values WA and WB, and assume that at the maturity time capital T, these portfolios has the same values, but at some time small t, which is less than capital T, the value of portfolio A is less than portfolio less or equal to the value of portfolio B. And then what is quite clear, we can sell B and buy A, and then we can invest this difference. So we can in saving account, so we can simply we get this difference and we save it. And if we have interest rate R, constant interest rate, then we have at the end time capital T. We have a profit which is equal delta T discounted according to our current interest rate. So it would be delta T multiplied with is of course possibility to become very rich, and it should not be the case for the ideal financial market. So it contradicts basic concepts of financial market, and so we have to, in this case, we have to require that the value of portfolio at any time, small t, before maturity, t are equal. Again, this is a simple example of arbitrage. There are many other examples where you have similar situation, but at least in this example you can derive very interesting conclusion. You could come to very interesting conclusion that in order to be non-arbitrage, for market to be non-arbitrage, any two portfolio with the same value at time capital T should have the same value at any other time small t, so they are simply equal. Okay. So for reminder, we assume that we have non-arbitrage, we assume this ideal financial market, and there are another requirement, so we require this ideal situation that there are no transaction costs, there are no taxes, no arbitrage. Then we assume that short selling is allowed, which is not always the case in the real markets. Sometimes short selling is not allowed, but in this case we assume it is possible. And okay, and now we come to our old story about forward contract, and we will try to figure out the price of the forward contract in this ideal situation, in the case of ideal financial market. And okay, I remind that capital K delivery price for strike, maturity date is capital is denoted by capital T. You have spot price of the stock ST, and the price of the forward contract B capital K capital T. And what we'd like to find, first we would like to find the price of this contract, and second we would like to find the forward price, which makes this contract worthless at time small t. And the following proposition said that the price of under all above conditions, requirements of ideal financial market, the price of a forward contract is equal to ST, spot price, minus delivery price, deflated according to the current interest rate R. For discount, I use sometimes discounted, deflated, but it's more or less the same. So you have to means mathematically it means that you multiply your K, you divide by 0 bond, and in this case 0 bond is equal to e to the power minus r tau. And the forward price can be easily deduced from this formula, because what is definition of forward price? Forward price is a delivery price which makes the contract worthless. So the V should be 0, so we have to find Ft in such a way that V of Ft capital T is equal to 0. And it's quite obvious that Ft should be equal as T spot price multiplied with e to the power tau, which is a bond price. So this is clear, yes? This because price multiplied discounted delivery price, and you have to find delivery price. So f t is defined with such k thus this equals 0. Means the case of constant interest rate and continuous compounding. Okay. So how to prove this proposition? On the next slides, 4 or 3 slides, you can see the proof. The proof is based on this heavily employs this non-arbitrage condition, non-arbitrage requirement. But first, this is continuation of this. I have forgotten this. Now comes continuation of this proposition for the case. First was the simplest case when you have no other costs. Now you have, if you, for example, have another cost. So if we denote by d, t as the value of all earnings and costs related to the underlying ST. So this can be some different costs. I will not go into details, but then we have to subtract all these costs plus earnings from the spot price, and the formula will hold true. And if you have so-called cost of carry, this is also some notion that I don't like going into detail. Some specific costs related to the delivery of this price of the stock, and in this case you have to multiply the spot price with e to the power d minus r multiplied with tau. So, but it is, the most important thing is to understand first part of this proposition, because if you understand first part, other parts are very simple. So, and I will concentrate only on the proof of the first part. The first part, how we can prove. So we consider two portfolios, A and B. What is the portfolio A? Portfolio A is a long position in forward contract with strike K, maturity capital T, and a long position in zero bond with face value K. What does it mean? It means the portfolio A, the price of the portfolio A can be written as a capital KT ST tau. This is the first part of the portfolio. This is a long position forward contract with strike K and maturity capital T. And then another part, second part of this portfolio A is zero bond with face value or nominal value K. We know that the bond price, the bond is e to the power minus I r tau. We have already discussed it, so basically this minus 1. Here, you remember that bond is always minus. If you discount, you divide by the bond. And this bond with face value 1, but unique bond, as you see, second part of the portfolio is a bond with face value or nominal value K. So you have simply, you have to scale it and multiply it with K. So this is first part of it. This is first part, second part is all. The second portfolio is a long position in the asset. So you have, simply you have your asset in your hands. So it is ST. And the price of these portfolios at time capital T is equal. Why? Because what do you have at time capital T? If your T equal to capital T, then you have that first tau is equal to 0, and second you have your price, contract price equal to 0. K is and you have S capital T. We have ST minus K. Okay, and then this is equal to K. This is equal to K. And this, and of course, if we have two portfolios with the same value at time capital T, according to our non-arbitrage requirement, we have to have the portfolios should be equal at any time before capital T. So they are equal, they are simply equal. So we have any time T. Equal 1 is time capital T, but this one over and so we have our proof. First part of the proposition and second part I have already proved here. price of the contract, and it's quite easy to get the forward price. Okay, the proof for second and the third part of the proposition is very similar. You have to consider different type of portfolios. So in the second part of the proposition, you have to take one portfolio, first portfolio A, exactly the same as before, but portfolio B, you should add value dt. You have to consider zero bond with face value dt. And again, due to this non-arbitrage requirement, you have that these two portfolios should be equal for any t smaller than capital T, because the value of portfolios are equal to capital T. And the third part is again the portfolio A is the same, and portfolio B. In portfolio B you include the carry costs. But it's not. So one example. So suppose you have. So we consider forward contract with discrete dividends. So we consider forward contract with 5-year bond. Bond price. He's written ST, but it's a little bit. Here's a little bit. It's a mixing notation. I mean, this is mixing notation because his zero bond is denoted by ST. We have denoted by DT, but I mean it is not quite consistent with the previous notation. But okay, this example is nevertheless interesting. So we have delivery price K, and we have time to maturity 1 year. It is interesting here, in particular, how the process with quantity dt is defined. Dt, if you have dividends, then you have some additional payments, and this additional payment should be included in this quantity dt. And how it is included? So you see here, you have, because you have coupon payments of 60, and you get these payments 2 times in 6 and 12 months. You simply take this your payments and discount them. So you divide by the corresponding bonds. What do we get? So we have 2 payments, 2 dividend payments. D1. We have interest rate. 2 interest rates. So you see here, interest rate is not constant. It's very important. So it's also somehow strange because on all slides it's always the case of constant interest rates always has been considered. Therefore, I have introduced non-constant interest rate, but here the interest rate is not constant. And so you have, at the time, 6 months, you have interest rate 0.09. You have your interest rate 1, if you measure everything in process of year, so you have to divide, so it is this is 0, 5, because it is a half year. And then you have 0, 1, you have 1, there's another payment, T2, you have discounted according to the current interest rate, which is equal 10%. So you have to write L2 is to be consistent. 6, 12 multiplied with 1. So these are your additional costs, and they are related to the dividend payment. And D1 in this case are equal to D2 equals 60. So now you can see what this formula, what does this formula for dt comes from. It comes from this general formula. If you plug in the values of d1, d2, r6, r12, and then according to the bar proposition, the price of that forward contract is equal to the spot price minus dt or earnings, additional earnings and costs, where you have no cost, we have no additional cost here, we have only earnings, this is due to dividends, and then we have minus K, delivery price, discounted according to the interest rate, and interest rate at the end, N is in this case capital T1, so we have 1 year, in 1 year we have our interest rate R12. And this is exactly what you see in the formula 4. And it's interesting that the contract, forward contract, the value of forward contract is negative in this case. It is due to this additional earnings from the dividend payment, and the forward price can be computed quite easily. This formula from the proposition. And now we are done. So this is, I would suggest that you maybe look at this example at home with more detail, because very important example that where you see how does it work, and you can see the concrete numbers of this can come out. Here is an example of forward contract with continuing dividends, but I will skip it because now there's some connection between future rate and forward, future price and forward price. I will skip it. So I will skip. Now I come to option pricing. have already mentioned there are two main so-called vanilla options, the call options and put options. And call options has the following pair function. Call option because this pair function, which is sometimes written as capital T minus K with plus. And this plus is exactly means that you have to take maximum these two values, 0 and S capital T minus K. This is exactly some notation in order to be concise. And for put option, have the payoff function is K minus S capital T. So in order to get from call option to put option, you simply interchange the strike price and S capital T, the price of the stock at time capital. And there is the notion of intrinsic value and intrinsic value of the option, not only for these two simple vanilla options, but this is general. If you have an option with pair function f as t, then the intrinsic value of this option pair of f of S capital T, where f is some function, then you have the intrinsic value of this option, f of S small t is called is intrinsic value. Time t. It's quite general for any option, at least European option. You can define intrinsic value as a function f of S small t. For non-European options, it's more difficult. When then we have number of other very important
Excuse me?
notions. Yes.
About the maximization equation, maximum of ST minus K and 0.
Yes.
There's like two values, but depending on the final value of the option, right?
Yes. You mean this one? This is pair function. Exactly. This pair function is defined because it's a European option. Any European option, it depends only on the behavior of your stock and only at the final time capital T. Yes, for any European option. But if you take another function ST, S capital T, you get another European option. Yes? So you can play with function f, and you get different European options with different payoffs. Yes?
What I mean is like if the payoff, if k is larger than st, then
It is zero.
I'll get like something negative.
No, it is no. It is zero
No,
because
I know, but
it is zero. Yes. And this is simply definitions of this. This is simply definitions. This is exactly this by definition, and this cannot be negative. Yes, because you take because your payoff. If your stock is k, you have zero. If your stock is larger than k, you have this one. This is exactly this payoff function, which cannot be zero, but in principle, your function f can be zero, can be even negative. I mean, there are some options where your function f can be negative. There are some options where this function negative, but I mean, these vanilla options, put options there, of course, because options is some type of you can say some type of insurance. You'd like to secure yourself from some losses due to some specific behavior of your stock. So in this case, what can you get in the worst case? In the worst case, you get zero. But if it would be, for example, without plus, then you can get a big loss, and then this would be negative. So if you are buy options, you can lose an ST, and so you have. And this is some kind of insurance that. So you bet against some specific behavior of the stock, but so you think that your stock will increase, the price of your stock will increase, but if it will decrease, you don't lose much. You lose only the price you have paid for your option. If you pay too much for your options, then you will lose much, but at least, because as I already told you, very important point, this is only payoff function, but your real gains should be compared with you have to subtract the price. So you have moved your curve downwards, and this would be exactly the shift would be exactly the price of your options that you have paid for your option. And this you can lose at the worst case, but not more than this, because of this plus. So there are more options in the money options, and at the money options, and there are out of money options. And they are classified according to the value of intrinsic value. So if you have options, you have your stock, S is time. So you have some specific time T0. And if your strike here, suppose that is the value of your strike, and we see that the time T0, ST is smaller than your strike price. When according to the definition, the call option, if we look at the call option, we see that characteristic value of call option is equal to ST minus K, and the theta is 0, so your option is out of money, according to the definition. And if your value of, if your strike price would be quite near to the spot price, somewhere here, then you can say that your option is at the money. And at the money options are most traded of the market. You have mainly out of at the money option, but you of course also have out of money option in the money options, and the recent years you have big problem with pricing your options, because the price of options in the money and out of money differs quite significantly from the price of the option at the money. This is a recent trend in the market, and this is due to some another more deep reasons, but okay, this is a definition, and you will encounter this definition very often if you read financial literature. Okay, now to some elementary properties of option prices. So first, option prices are generally non-negative, but there are some options, as I told you, they can be negative, but it requires some specific interpretation. If you get negative price of option at some losses, but usually they are non-negative, then the price of European option is at maturity T is equal to the price. I think that is not clear, but usually, as I told you, the price of European option is usually less than the price of American option. Not at maturity capital, because at maturity capital T, you have your payoff function, yes? And you have payoff, the same payoff in the case of American option or European options. If you have two options with the same payoff, one option is American option, another is European, then you have, of course, the same value at the maturity time. But the price of European options at any time before maturity is less than the price of American option. And it is clear why, because if you buy European option, if you buy American option, you have more flexibility. You can exercise at any time before maturity, and European option you can exercise only at the time, at the maturity time, so you have more flexibility, and you have to pay for this flexibility, and therefore the American option is usually more expensive. This interesting value is more expensive. Now some simple properties of American options. So if you have two American options with different maturities, then you have the following. This is if you have American call options, and the price of American call options with a smaller maturity is less than the price of American option with a larger maturity, and for put option you have another inequality. For American options, of course, I will maybe later on I will devote maybe 1 hour or more about pricing of American options, and I will give more details about the properties of American options. But in principle, it is clear if you have the American option, you have maturity time, the spot price, if you can exercise at any time before maturity, capital T, so you can exercise at any point on this interval, but usually on the market you encounter only Bermudian options, or options that can be exercised not every day, because the trading takes place usually not every day. So you have some specific days where you can exercise your option before maturity, capital T, and this is quite clear that the price of your American options should decrease if you go further, or if you at least, for example, if you have your exercise possibility, suppose we have n exercise possibilities here. So we have divided our interval small t capital T into 10 sub-intervals, and we have exercised at any of these 10 points, and assume that we have delete 1 point from this. We say we cannot exercise at this point, but we can exercise at the remaining points, that the price of your option is clearly, your new American option would be clearly less than the price of the old option, because you have less flexibility. Now you cannot exercise everywhere on this grid, but only one point less. And so this is an interesting property of American options, that more exactly Bermudian option, but on the market you mainly see Bermudian type options. You don't see there's some ideal situation where you can exercise everywhere or each time. Okay, so as I already told you, the price of American option is always bigger than the price of European options. The call prices are monotone decreasing function of strike price. It's also clear, but maybe I can give some hints. At least the price, the call price, as I will explain later, is an expectation under some measure of the pair function. And the pair function, for example, in the case of call prices, is this is a general formula. I will not now specify what kind of measure, what is expectation, but there exists a measure, and such that the price of the option is more exactly, should be more exact. This is quite exact. And as you can see, the second property, that the call price a monotone decreasing function is strike. If you look at this formula, you will see it immediately, because if strike increases, so your pair function, of course, decreases, and according to this continuity of monotonicity of expectation, you also see that the expectation will be at least less or equal than the expectation with largest strike. What we have, you can write it STK, and this STK1 will be less and or equal to STK2 if K1 is larger than K2. Similarly, the put prices are monotone increasing function in strike price, because for put prices, again, we have the similar formula. K minus S capital T. And you see the strike increases, and this quantity increases, and the expectation cannot become less, at least. So you have now another important property is that we are continuous in this. And this property of put call parity, this connection between put price and call price. And the connection is very simple. So it is this proposition. Is again is process dt is quantity dt is used. This is all costs and earnings. But the main, I would say, we can skip this dt in order to understand the main ideas behind this put call parity. So in the simplest case, no dividends and no additional costs, we have the CK. It's also not quite consistent with my notation, but I think you will understand that the full price is, it of course depends on the strike price, depends on capital T maturity, it depends on spot price ST, and depends on difference tau capital T minus T. And according to this proposition, it is equal to put price of the put option plus spot price minus K to the power minus R tau, which is again bond price, scale with K, that is zero bond with space value K. So this is a put call parity. This proposition is extended to the case of additional costs, and the second part to the case of so-called cost of carry. And how to prove it again, we have to apply our non-average requirements, non-average conditions. So we again consider two portfolios. But here we have given, so one portfolio is consisting of long put at the price of so we have long put, short call, short bond, and long asset and short bond. Okay, we forget about DT, and this portfolio is written here in this table. So we have again long put, it means we buy put, short call we sell call, and the right part of the table you see the value of this portfolio in time capital T. So you have time capital T. You have of course your put price, you have your payoff function, the payoff at the end, because it is long, we buy. In the case of call price, we have payoff of call with negative sign because we sell the call option, and the short bond we of course have at the end of bond we have here 0 because the time capital T is 0, so we get minus K. So again, short bond, we sell bond, so this is why we have minus here. Then we have long asset, this is simply, we have our asset, this is S capital T, and if we add all these quantities, right part of the table, we get 0. So we have that our portfolio is 0 at time capital T. And this means, according to our non-arbitrage requirement, that the value of portfolio should be 0 at any time before capital T. And this means that it is 0 always. It's always 0. And we have exactly this condition. This exactly if you put this call price on the right side and write 0, then you see that call price will be just negative sign, and all other terms are exactly terms in the left part of this table. So because we have proved this proposition, and again I stress that you can always add value for this quantity dt. That changes nothing. It is only some additional quantity, and you also can consider the cost of carry. It is not so important. And, okay, this proposition unfortunately does not hold for American option. For American options, there exist different extensions. They have appeared quite recently in the recent papers, so they are not so simple. And why it is useful? I mean, what is this put call parity for? Is this? I mean, it is this. Of course, it is first. It is connection between call and put price. But it is useful because sometimes you observe on the market only call prices, or you observe call prices for some specific strikes and put prices for other strikes. And this put call parity proposition allows us to compute unknown put prices from the call prices, or otherwise around, you compute call prices from put prices. It is always possible if you know ST is the spot price, you know K is the strike price, and you know the bond. elasticity, that's the price of American and European option is convex function in a strike price. I will not touch its proof. You can read it. This is quite simple. Again, you can simply construct different portfolios and then consider you have to construct portfolio in such a way that is equal some specific value at maturity time, and then you deduce from the non-arbitrage conditions that is equal to this value at any time before maturity. So the idea is the same. Also, there's another proposition. This is another property of European options, vanilla European option, and this is concerning the behavior of the derivatives of this option. According to strike, and also very important, it will be important later on, because of this derivative of the options, of the put option or call option, plays a crucial role for deriving implied volatility and another interesting quantities on the market. But I think that now I will finish. And next time I will explain, maybe remind